In 2026, one of the world's most respected Nobel Prize-winning physicists issued a stark warning. After reviewing the latest James Webb Space Telescope data, he said, "It's a different universe, not slightly different, not a minor adjustment, fundamentally different from the one we thought we understood. What JWST has seen, galaxies forming too early, structures too massive, physical processes happening too fast, has forced even the most conservative cosmologists to admit that our standard model of the universe is in serious trouble. This is Galactic Origin's most comprehensive deep dive yet. Over the next several minutes, we will explore the specific strange things JWST has revealed, the Nobel laureates' warning, the growing crisis in cosmology, and what it might mean for our entire understanding of reality. The warning didn't come from a fringe theorist. It came from a Nobel Prize winner with decades of respected work in cosmology. His statement reflects a growing consensus among many leading researchers. The James Webb Space Telescope is not just refining our picture of the early universe, it is breaking it. The anomalies are piling up. Galaxies that appeared too mature, too massive, and too chemically enriched when the universe was only a few 100 million years old. Star formation happening faster than models allow. Supermassive black holes already in place when they should barely have begun forming. These are not small discrepancies. They strike at the heart of our standard Lambda-CDM model. Let's be clear about what JWST has actually seen. In multiple deep field surveys conducted in 2025-2026, JWST repeatedly found galaxies that, according to pre-launch models, should not exist yet. Some appear to have stellar masses comparable to the modern Milky Way, when the universe was less than 500 million years old. These observations directly contradict the standard hierarchical formation timeline that has been the foundation of cosmology for decades. The Nobel Prize winner's warning was not hyperbole. It was a sober assessment after carefully reviewing the data. He and many colleagues now believe we may need fundamentally new physics to explain what JWST is showing us. The early universe appears to have been far more efficient at forming complex structure than our models predicted. Something important is missing from our understanding, and that something could reshape cosmology as profoundly as the discovery of dark energy did in the late 1990s. This is not just another incremental discovery. It is a potential paradigm shift. The James Webb Space Telescope has forced us to confront the possibility that the universe we thought we knew so well is, in important ways, a different universe than we imagined. So what exactly has JWST seen that is so strange it prompted a Nobel Prize winner to say, "It's a different universe"? The most shocking discoveries fall into several categories. First, there are the ultra-early massive galaxies. In multiple deep fields, JWST has found galaxies with stellar masses comparable to the modern Milky Way, existing when the universe was only 300 to 500 million years old. According to standard models, there simply had not been enough time for gravity to pull together enough gas to form such massive systems. These galaxies are not small, chaotic protogalaxies. Many show well-developed structures, disks, bulges, and even hints of spiral arms, far earlier than anyone expected. Second, these early galaxies show surprising chemical enrichment. They contain significant amounts of heavy elements that require multiple generations of stars to produce. Second, these early galaxies show surprising chemical enrichment. They contain significant amounts of heavy elements, oxygen, carbon, nitrogen, iron, that require multiple generations of stars to produce through fusion and supernovae. In the standard timeline, there simply wasn't enough time for these metals to build up. Yet JWST spectra show they are already present in substantial quantities. One 2026 research paper states, "The level of chemical enrichment observed suggests star formation and stellar evolution proceeded at rates far exceeding theoretical predictions." Third, there is the problem of supermassive black holes. JWST has found quasars powered by black holes of hundreds of millions to billions of solar masses existing when the universe was less than 700 million years old. Growing a black hole to that size through normal accretion should take billions of years. The fact that they already exist so early suggests either extremely rapid, super Eddington accretion, and here, or the existence of heavy seed black holes formed through direct collapse in the early universe. These three anomalies, massive early galaxies, unexpected chemical enrichment, and overly massive black holes, form a coherent crisis. This is what makes the situation so unsettling for many cosmologists. It's not that JWST found one weird object. It's that almost every deep field it looks at shows the same pattern of impossible, early maturity. The anomalies are systematic, not isolated. This suggests something fundamental is missing from our theoretical framework, a missing piece that could force us to rewrite major parts of cosmology. The warning, "It's a different universe," is not hyperbole. It is a sober acknowledgement that the data no longer fits comfortably within the standard model. The anomalies JWST has uncovered are not minor inconsistencies. They represent a growing crisis at the heart of modern cosmology. For decades, the Lambda-CDM model, our standard picture of the universe with dark matter, dark energy, and hierarchical structure formation, has been remarkably successful. It explained the cosmic microwave background, large-scale structure, and the accelerating expansion of the universe. But the 2025-2026 JWST data has exposed cracks that are becoming increasingly difficult to ignore. The early universe appears to have been far more efficient at forming complex structure than our models predicted. This is not just one or two weird objects. Across multiple independent deep fields, JWST consistently finds the same pattern: galaxies that are too big, too bright, too chemically mature, and too structurally developed for their cosmic age. The warning is clear. Either our understanding of the early universe is seriously incomplete, or the standard cosmological model itself needs major revision. When a respected Nobel laureate says, "It's a different universe," the scientific community listens. His statement reflects a growing view among many experts that the standard model's assumptions about star formation efficiency and the pace of structure formation may be fundamentally flawed. Some researchers are exploring modifications to dark matter properties. Others are looking at new early dark energy models, and a few are even considering more radical ideas. This crisis is both challenging and exciting. It means cosmology is entering a fertile period where major breakthroughs are possible. Just as the discovery of dark energy forced us to rewrite the book on cosmic expansion, JWST's data may force us to rewrite the chapter on how structure formed after the Big Bang. The Nobel winner's warning is not a declaration of defeat. It is a call to embrace the unknown and push our theories further. What makes this moment so powerful is that it represents science at its best, when observations refuse to fit our favorite models and force us to think deeper. The James Webb Space Telescope has not just taken prettier pictures. It has shown us that the early universe was far more efficient, far more structured, and far more surprising than we dared to imagine. And that realization is both terrifying and profoundly inspiring. When observations refuse to fit the standard model, scientists have two choices: tweak the existing framework or consider more radical revisions. In 2026, both approaches are being pursued with urgency. The most conservative path involves modifying parameters within Lambda-CDM. One popular idea is early dark energy, a form of dark energy that was stronger in the first few 100,000 years after the Big Bang. This could have accelerated structure formation, allowing galaxies and black holes to grow faster than expected. Another approach involves self-interacting dark matter. If dark matter particles can interact with each other beyond gravity, it could change how small structures form and merge, allowing faster early galaxy assembly. More radical proposals are also gaining attention. Some theorists are exploring the idea that fundamental constants, like the strength of gravity, may have varied in the early universe. Others are revisiting cyclic cosmology models, where our Big Bang was not the absolute beginning, but a transition from a previous cosmic aeon. In these models, some structure or information could carry over, explaining the surprising maturity JWST sees so early. The Nobel Prize winner, who issued the warning, has been particularly open to these ideas. Let us explore one particularly intriguing thought experiment. Imagine the universe is cyclic. Each aeon ends in a smooth, empty state, then transitions into a new Big Bang through some mathematical rescaling. In this framework, the impossible early galaxies JWST sees might not be forming from scratch. They could be seeded or influenced by subtle remnants from the previous aeon. This would explain both the rapid structure formation and the surprising chemical enrichment. It would also align with the Nobel laureate's sense that we are looking at a different universe, one with a much richer, deeper history than a single Big Bang allows. Not everyone agrees with these radical ideas. Many cosmologists argue that the standard model can still be salvaged with relatively minor adjustments. The debate is healthy and vigorous, exactly how science should work when confronted with unexpected data. What is clear in 2026 is that JWST has created a genuine inflection point. The data is too compelling to ignore, and the community is now actively exploring a much wider range of theoretical possibilities than it was 5 years ago. The Nobel Prize winner's warning, "It's a different universe," captures the spirit of this moment perfectly. We are no longer fine-tuning a successful model. We are confronting the possibility that key assumptions at the foundation of cosmology may need to be re-examined. And that is both a daunting challenge and one of the most exciting opportunities in modern science. The James Webb Space Telescope has done something remarkable in 2026. It hasn't just taken clearer pictures. It has forced an entire generation of cosmologists to confront the possibility that the universe we thought we understood so well is, in important ways, a different universe than the one described by our standard models. The Nobel Prize winner's warning was not an overreaction. It was a sober acknowledgement of what the data is telling us. The early universe was far more efficient, far more structured, and far more surprising than we had any right to expect. This moment represents science at its most honest and exciting. The James Webb Space Telescope has shown us strange things. It has challenged our models and humbled our assumptions. But it has also reignited our sense of wonder. Whatever the final resolution turns out to be, whether it requires modest adjustments or a complete paradigm shift, one thing is certain: the universe is more interesting than we thought, and we are lucky enough to be alive at the moment when we are beginning to see that truth with new clarity. Thank you for joining me on this long journey through one of the most exciting developments in modern cosmology. What do you think? Is the universe different in a fundamental way, or can the standard model still be saved? Drop your thoughts in the comments. If you love these extended explorations into the biggest questions of cosmology, please hit like, subscribe to Galactic Origins, and turn on notifications so you never miss an episode. This is Galactic Origins, going deeper than anywhere else. Until next time, keep looking up with curiosity and courage.